Okay, today we'll talk about the first law of thermodynamics. Okay, the first law of thermodynamics is a conservation of energy principle. And with heat, where we'll keep track of heat as well. So for instance, you have learned conservation of mechanical energy in, in physics 1. Mechanical energy was kinetic energy plus potential energy. Initial was equal to kinetic energy plus potential energy, final. Okay, so this, all kinds of energies are conserved if you can keep track of all kinds of energies. So we had this law when friction was not present, so heat was not in play. Okay, so we were considering very, very restricted kind of systems, phenomena. Yeah, friction was not acting in our thing, and so this, we said mechanical energy is conserved. Okay. So an example would be, if a marble rolls down a hill without friction, what will it do? It'll keep oscillating forever. That's mechanical energy being conserved. A simple pendulum will keep swinging forever if there's no friction. Now we have graduated to the fact that, well, there's friction present in nature, and we're going to keep track of heat as well. Okay? So that's the first law of thermodynamics, and here's the statement of it. Okay. Q is, okay. So what this is, so here's your system. Okay, I'm going to erase some of this stuff. Okay. Here's your system. Okay. What this equation says is Q is the heat added to the system. Okay. E is the internal energy of the system. Okay. So the heat added is change in internal energy minus the work done by the system. Okay, so Q is the heat added to the system. W is the work done by the system. Okay. And delta E is the change in internal energy of the system. All right, so let me give you an example. Let's say you eat 3,000 calories today, and you do 1,000 calories of work. Where did the other 2,000 calories go?
Stores fat.
There you go. That was the increase in internal energy. Okay. You didn't eat anything today. You did 2,000 joules of work. What happened?
You earned 2,000 joules of stored energy.
Right. So this was 0. You did work. Your internal energy decreased by that amount. Okay? Yeah. So that's what this, okay. Oh, I'm sorry. So change in internal energy is Q minus W. That's the equation. All right. So you didn't eat anything today. You did 2,000 joules of work. Your internal energy decreased by 2,000 joules. Okay. So that's the first law of thermodynamics. Okay. Yep.
I mean, Q and W are like that because, gaining heat is negative or
So the sign convention, our friend is asking the following. So this equation, the sign convention for this equation, and some engineers will write delta E equal to Q plus W and so on, then the sign convention is different. Okay. I don't know if you guys have taken a thermodynamics class yet, okay? But so this is the sign convention I like, and this is what most physicists use. Okay? So in this sign convention, if heat is added to the system, Q is positive. We look at it from the system's perspective. If the system does work, W is positive. Yeah? And if the internal energy of the system increases, delta E is positive. Okay, so that's the sign convention. So what's the first law of thermodynamics?
The change in energy is equal to energy put in.
Minus the work done. Yeah. So it's a conservation of energy principle with heat included. Okay, here's another way to remember it. I'll give you a financial analogy. This is your bank balance. This is your earnings. This is your spendings. Okay? Your earnings minus your spending is the change in your bank balance. Yeah. All right, now before we get into the chapter, let me show you a very neat tool. Okay? Okay. So what I'm going to do is I'm going to hold the pressure constant. Okay. Here's a gas. And there's the temperature. What I'm going to do is I'm going to heat it. Okay. I'm going to hold the pressure constant and heat it. What happened?
Volume expanded.
Okay, the volume expanded and the temperature rose. Okay, so that's what happened. Here's a PV diagram. That was the initial pressure and volume of the gas of the system. And then I added heat. The pressure was constant, the volume increased, and the system went from here to there. See that process that I just showed you? There is that process in this diagram. So here's a very neat tool to represent that process. Okay. And there's the temperature, there's the pressure. I'm going to heat the gas again, and this time I'm going to keep the volume constant. And watch the temperature and pressure. They both increased. There was the initial state of the system. The final pressure was higher. Okay. Oops. And there's the process. Okay. All right, so PV diagrams are very useful to represent various processes. What was this process? Well, it was some kind of process. Yeah. And we'll tell you about specific processes. So what is this process? What can you say about this process?
Constant pressure.
What was this process?
Constant.
Constant volume. Okay. And so what is this process? I don't know. Okay. And we can't say anything about it. I mean, I can't say something was constant. But we'll introduce various processes to you where something is constant. Okay, so for instance, what is the ideal gas equation? PV equal to nRT. Okay. So P equal to nRT divided by V. Okay, let's do a process where temperature is held constant and the amount of gas is constant as well. You won't let the gas leak out or anything, all right? So this guy will be constant. And what is the graph of y equal to c over x? It's a hyperbola. Okay? So the graph will look like this. So here you've learned another thing. Okay, in this process, what is constant? Temperature is constant. Yeah. All right, so if you start off at a higher pressure, okay, if the pressure is higher, that means the temperature is higher. Okay? So there's another parabola. This is a low temperature, this is a higher temperature for the same. Okay? All right. So we have these tools. All right, now let's do the following. Here's a block of metal, iron. Okay. You saw that when I was heating the gas at constant volume, you represented that like how? Like that. Okay. All right, I'm going to heat this thing. I'm going to heat it so I'm heating this block of iron and it's surrounded by atmospheric pressure, so I'm heating it at constant pressure. Its volume is changing, but its volume is changing ever so little. I can't even draw it on that diagram. Okay? So as soon as you see PV diagram, they're useful when your system is a gas. If your system is a solid or a liquid, the PV diagrams are not useful. Okay? So whenever you see PV diagrams, you're trying to represent as a process. The system consists of a gas and it's undergoing some kind of process. Okay? So you use PV diagrams for that. Okay? Well, we'll use PV diagrams. We'll come up with thermodynamic laws. Then what kind of systems do thermodynamics laws apply to? Will it apply to solids and liquids?
Yes.
Yes. All right. All right. So thermodynamic laws will apply to all kinds of systems as long as it's a large particle system. Yep. All right. All right. Here's the model of a solid. Okay, so it's at room temperature. What is going on? These atoms are vibrating at their location. Okay, and if you heated this gas, the distances would increase, the potential energy would increase, and so on. Okay, and also the potential energies change is fluctuating as well. Anyway, so there's internal kinetic energy and potential energy. So now, if you bring this block in contact with a colder substance, a temperature, an object at a colder temperature, so this is hot, what will happen?
Transfers energy.
Yeah, heat is transferred. And heat is this internal random kinetic and potential energy that's being transferred. Okay? And so heat transfer happens as long as the temperature of this is higher than this. Okay? So, and when will heat transfer stop?
When they're in equilibrium.
Eh.
It won't. It'll keep going, just the net will go to zero.
Yeah, net will be zero. Okay, so till the temperature equilibrates. Okay. Now, heat can be used to do work. Okay. And we do this in a lot in our lives. When you drove here to class, the gas in your gas tank, you burned that, you generated heat, and converted that to motion. Okay. Okay. So this guy has potential energy, and when he falls, 100% of that can be converted to kinetic energy. You have heat, and in general, only about 20% in your car anyway, only about 20% is converted to kinetic energy. Okay. So, I mean, we use these kinds of devices in our lives, and you will learn that only heat is the worst form of energy because this is the least percentage of conversion to kinetic energy. Okay. You can go the other way. You can convert kinetic energy to heat. And what fraction can you convert kinetic energy to heat?
Almost full.
100%. Not almost full. Yeah. You can convert all of it to. Okay. All right. So heat can be used to do work. It can be transformed to any other form of energy. In a car, heat obtained from burning gasoline is converted to mechanical energy. Okay. It's just that that conversion is not very efficient. Okay. And in the next chapter, we'll give you an upper limit on the conversion. Okay. So what are things that convert heat to work called?
Thermodynamic system.
I'm sorry?
Thermodynamic system.
Heat engines. Okay. They're called heat engines. And we'll learn about the maximum efficiency possible for a heat engine. Yeah. All right. What are thermodynamic systems? Systems with many particles. Okay. So here's a system, here's the boundary of the system, here's the surrounding. Okay. Again, system, boundary, surrounding. Open and closed system. Okay. So what we refer to is the following. Here's a system. The system can do work. Heat can flow into the system, and so on. And this is the number of particles in the system. Okay. If the number of particles remains constant, that's a closed system. If this system exchanges particles as well, then it's an open system. Okay. So here's a closed system. The amount of water inside the pressure cooker remains constant. Here's a kettle. That's an open system. Okay.
I thought a closed system also prevented exchange of heat or anything.
So now we're specifically, what we're referring to is the number of particles. Okay? So that's the definition. Reversible and irreversible processes. Here's a hot cup of coffee. I set it on the table here. What happens? Well, the room is cold, and if I set it on the table, after a little while, the coffee will get cold, and the room is also cold. Okay. Now, if you can bring back the system, this to exactly the original state, then that is a reversible process. Okay? So let me write it like so. This is the system, initial state of the system. Oh. And this is the environment, initial state of the system. And some process happens. This is the final state of the system. And this is the final state of the environment. Okay? Now, if you can bring this back to exactly the same, both the system and environment to the original state, that's a reversible process. Okay? Did you guys understand that? You have to bring the system and the environment to the original state. So here's a statement. All naturally occurring processes are irreversible. Okay, I'll give you a concrete example so you can have this in your mind. All right, we'll get a bunch of ice from your freezer and put it on the kitchen table. What will happen? It's going to melt, okay? How did it melt?
Heat from the table moved into the container.
Yeah, heat from the kitchen moved into the table, okay? Into that thing. Well, I can refreeze this water. I can just stick it in the fridge. Okay? I can refreeze this water. So I'll refreeze it, but to refreeze, to run the fridge, you have to do work. And that work turns into, the friction turns into heat. So doing work, the kitchen is hotter now. It's hotter than before. Okay. Well, you brought back your system to the original state, but the environment you couldn't bring back to the original state. So that process was irreversible. Okay. You can't go back to the original state. Okay. All right, so a reversible process is one. A reversible process is one in which the system and the surroundings can be returned to the initial condition from the final state. Okay? And you can't do that for any natural processes. All natural processes are known to be irreversible. All right. Here's a mass M. I apply a force on it against gravity and lift it up. How much work did the force do? mgh. Okay? So when you lift an object up, you're doing work. Okay? Can a gas do work? Yeah, so here's a piston, we saw this. We'll put a mass there, we'll heat the gas. If the piston is movable, it'll lift the object up and it'll do work. So an expanding gas will do work. Okay? So let's see how much work will it do precisely. Okay? Work done is force times distance moved. Okay, so an infinitesimal amount of work is force applied times that small distance the force moves. Okay, the object on which the force is acting moves. So dW is that force is pressure times area times dr. So we are looking at the gas expanding. Okay, there is the force, pressure times area, and the gas expanded such that the piston moved that much. A times dr is the increase in volume of the gas. Okay? So what this expression is telling you is the amount of work the gas did was the pressure of the gas times the increase in volume. Okay? So if dV is positive, the gas did positive work. If dV is negative, the gas did negative work. Okay? So that's how much a gas That's how much work a gas did when it expanded. So again, the sign convention is work is positive when the gas does work, and negative if the work is done on the gas. Okay. Again, in your thermodynamics classes in engineering, you might be doing the opposite sign, but physicists like this sign. Okay. All right, so there is the infinitesimal amount of work done. And the total work done in going from the initial to final state is just the sum of all these little pieces of work. That's an integral. Okay. So if you plot pressure versus volume, and you saw that each curve is some kind of process, right? We saw that. Without pressure versus volume. So here is this initial state of the system, okay? And the system is made of some kind of gas, okay? And here is a process. Okay? So if you now if you ask me, so you see the gas has expanded from the initial volume to that much. Okay? And if you ask me how much work did the gas do, now we have an answer. The work done is that, which is the area under this curve. Okay? Now let me ask you this. So here is the initial state of the system, here is the final state of the system. How many different ways can you get there? Infinite. Yeah. And you see the work done is path dependent. Yeah. Okay. So this illustrates that you're going from here to there in all different ways. Okay. And the work done is path dependent. So here is the first law of thermodynamics. Yeah. What does this say? Change in internal energy of the system is the heat added to the system minus the work done by the system. Okay. What kind of systems does it apply to? All thermodynamic systems. Okay. Okay, here is the sign convention again. You might see a different sign convention, but Q is positive for this equation. The sign convention for this equation, we look at things from the system's perspective. Q is positive when heat is added to the system. Q is negative when you remove heat from the system. W is positive when the system does work. And if you do work on the system, then that's negative. Delta E is positive when the internal energy of the system increases. Okay? So that's the first law of thermodynamics. Okay? Now, the rest of the chapter, what we're going to do is, we're going to introduce various processes to you guys, and we'll tell something about each term for those processes. Okay? And then we'll do some other stuff too. Okay, here's an isotherm. An isotherm, iso means constant, and therm is temperature. So these are processes where the temperature is constant. Okay. Here's what is constant in this process? Pressure. That is called an isobaric process. Here's a process where volume is constant. It's called isochoric process or isovolumetric process. Right? So isobaric, isovolumetric. Now here's a process that is connecting two isotherms. Okay? So, and this is an adiabatic process. Okay? And in this process, no heat is exchanged. So you're not exchanging heat with the environment. And if you expand, so for instance, you guys have used a bicycle pump. Is that a no, that's not a bicycle pump. Okay. When you expand, if you expand, pull up the pump real fast, okay, the volume of the gas inside is increased while you're also pulling in air, but we won't worry about all of that. So the gas expands and it'll cool down. Yeah. If you're not doing exchange, absorbing heat from the environment. In an adiabatic process, what is constant? And we'll tell you that at the end of the chapter. It's a slightly complicated thing. It turns out that PV to the power of gamma is constant. Okay. See, in physics, we like to say what is constant in various things. Okay, so I'll take you back to physics 1. Here is a roller coaster, frictionless roller coaster. And here's a cart going on the frictionless roller coaster. When it goes downhill, it's speeding up, slowing down, speeding up, and all. But is there something that remains constant in this process?
Total energy.
Mechanical energy, okay? Potential energy plus kinetic energy remains constant. Okay? So that's what we like to do in physics. We like to say, hey, here's stuff happening. This stuff is constant. We're doing the same thing here. Okay? In an isovolumetric process, volume is constant. Isobaric process, pressure is constant. Isothermal process, temperature is constant. In an adiabatic process, when no net heat is being exchanged, this fellow is constant. And I haven't told you what gamma is, but I'll tell you that. All right, so this is what we want to keep in mind. What is that? That's the first law of thermodynamics. Okay. This is a cyclic process. What does a cyclic process mean? The system starts at some initial point, it'll go through a cycle and come back, end up in its initial state. Why do we talk about this? All the heat engines go through cyclic processes. So, for instance, a piston. So here's the piston in your car. What do? You inject fuel, air, then compress it, then burn it. Burn the hot mixture. It does work, and then after the exhaust go out, then you come back to the initial state. Okay. So I'll show you a simulation of that. Okay. So a lot of your heat engines go through cycles. Okay, so here's a cyclic process. The internal energy is a state function, meaning the internal energy just depends on the state of the system. So if you come back to that original state, the change in internal energy is 0. Okay. But see, so the work done during this process was the area under this curve. The work done during this process was negative. The work done during this process was 0. So the net work done was that area minus this area, which was equal to this area. You did positive work. If you go clockwise, you did positive work. So where did the energy come from to do the work? The internal energy change is 0. So if you did 10 joules of work, that means you absorbed 10 joules of heat. Okay? So the heat absorbed is equal to the work done. Isothermal process, what's an isothermal process?
The temperature remains constant.
The temperature remains constant, okay? So for an ideal gas, I'll just quickly write down the internal energy. Internal energy is number of particles. F is the degree of freedom, and each degree of freedom contributes 1/2 kT to the energy. So this is the total energy of the system, F over 2 kT. What is an isothermal process?
Temperature remains the same.
Temperature remains the same. If the temperature remains the same, internal energy is the same. Okay? So during an isothermal process, the change in internal energy is 0. Okay? So again, like the cyclic process, any work done is equal to the heat absorbed. Yeah. You guys understanding what's going on here? Okay, so keep that in your mind as we are doing this. An adiabatic process. So you're either compressing or expanding the gas, and you're not absorbing any heat. Okay, so if the gas expands and you've done work, then the internal energy decreases by that amount because you've not absorbed any heat. Q is 0 in an adiabatic process. Okay, so the work done, if you do positive work, internal energy decreases. This will be negative. Negative times negative will be positive. Okay. Okay, so again, it's like in everything. How do you get to know something? I mean, how do you get to know a person? You have to know something about them. So, how do you know about a process? You say stuff about the process. Okay, here's an isothermal process. What have you said? Okay, how did we identify it? Temperature is constant. And now we're going to tell you another thing about it. In an isothermal process, I can tell you exactly how much work is done. Again, I can calculate this area. So here's what we're going to do. So here's an isothermal expansion. There's the initial state, there's the final state. Initial volume, final volume. Okay. P is nRT over V. That's our system consists of an ideal gas. Okay. And the work done is P dV. Okay. P is nRT by V dV. Now this integral is easy to do. That's just log V. Okay. And so the work done is nRT. Remember, we kept temperature constant, so that was a constant. We pulled it out. Log V, V initial to V final. There's the work done in an isothermal process. Okay, what if the final volume was equal to the initial volume? You did no work. V final equal to V initial, that's 1. Log of 1 is 0. Okay. What if the final volume was smaller than the initial volume?
You expanded work or output work.
You did negative work.
Yeah, but it's the environment, the work in the system.
Yeah. So when V final is less than that, this number is less than 1. Log of that is negative. The system did negative work. Okay. All right, so we gave you another expression. Isobaric, isochoric, and so on. In an isobaric process, that's easy, very easy. The work done is the area under that curve, which is just the area of this rectangle. It's P times change in volume. Isovolumetric process, the area under that curve is 0. Work done is 0. Okay, what are these? Isotherms. Temperature is constant. We have the same amount of gas. Okay? The temperature is constant. Which one is warmer? Is this one warmer or this one?
The first one, or the higher.
Yeah, this one is warmer. Okay, so delta T is positive. What we're going to do is the following. We're going to take the gas and warm it up. We're going to, if we warm it up along, we'll warm it up along this path. Along that path, what has happened?
You kept the volume constant.
You kept the volume constant. So the gas didn't do any work. All the heat added went into speeding up the molecules. Okay? When the temperature is that high, the average kinetic energy is a specific value. When the temperature is this much, the average kinetic energy per molecule is a specific value. So when you went along this path, you didn't do any work, all of the heat went into speeding up the molecules. All right, how about if we go along this path?
Not only, well, since pressure is constant, not only did you speed up molecules, you had to do work to increase the volume.
Exactly.
At the same time.
So you did work as well. So which path did you have to spend more money on?
Increasing the volume, because you had to do work.
This one. Yeah, 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 yeah. So you spent more heat in warming the gas through the same temperature along this path. Okay? So here's one thing we've learned. Heat added to a system is path dependent. Okay? How many different paths are there to get from point 1 to point from one curve to another? Okay, can you be a little more specific? Infinite. Okay? The heat added is different on each path. Okay? What we'll do is we'll tell you how much heat is added along that path. That's a constant volume process. And that path, that's a constant pressure process. Okay? We talked about this. What is the most convenient way to measure how much gas you have? Hmm? Yeah, and so the number of moles. Okay? Solids and liquids? Mass. Okay. So we define molar specific heats. Okay? We're going to add heat at constant volume. This is the amount of gas you have. And specific heat at constant volume is that. And this is the rise in temperature. This is heat added at constant pressure. This is the gas. This is the amount of gas you have. Specific heat at constant pressure times that. So what we have learned now is, given an amount of gas, if you raise its temperature at constant pressure, you're adding more heat because this number is bigger than that number. Okay? Why was this number bigger than that number? Because during this process, you had to spend some money doing work and speeding up the molecules. Okay? And you will learn that Cp minus Cv for all ideal gases is R. That's, that's a pretty neat statement. Okay? How many different gases can you think of? More than 100. Okay? And as long as they're dilute, they behave ideally. And for all of them, Cp minus Cv is R. So the work done by a gas during a process is path dependent. This is path dependent. This is not path dependent. So since this is path dependent, that's also path dependent. Okay. All right, so we're going to heat the gas from this temperature to that temperature, and we're going to see how much heat is needed along this path and along this path. Okay, only two of the infinitely many possible paths. Okay, so this is, we'll call it QV, QP. Okay, that's how much we are going to warm it. Okay, so we define two specific heats for gas. CV is the molar specific heat at constant volume, and CP is the molar specific heat at constant pressure, and CP is greater than CV. Yeah. Okay, I'll show you the derivation here. So we've already done this before. The internal energy of a gas is, let's say each particle has F degrees of freedom. How much does each degree of freedom contribute to the energy? This is an equipartition of energy statement. Very good. 1/2 kBT. Okay. K is the Boltzmann's constant. And then if you have n particles, that's n. Okay. I'm going to write this like so. N is the number of particles, and that's equal to the number of moles times the Avogadro's number. And this Avogadro's number times Boltzmann's constant is the gas constant. Yep. So it's F by 2 nRT. And CV at constant volume is defined as 1/n per mole change in internal energy with respect to time, derivative of change in internal energy with respect to temperature. And derivative of this with respect to temperature is just this guy. Okay. The n cancels, so CV is F over 2R. So for an ideal gas, CV, the molar specific heat at constant volume is F over 2 times R. Okay. CV, so for a monoatomic gas, how many degrees of freedom does a monoatomic gas have? 3. So it's 3 halves. Okay. So what we are doing here is, in this process, adding heat and along a constant volume process. And CV is that. So for all monoatomic gases, what we have found is CV is 12.5 joules per mole per Kelvin. What does this mean? If you take 1 mole of helium and you warm it by 1 degree Kelvin, this is, you need 12.5 joules of heat. How much heat do I need if I take 1 mole of argon? So, yeah. So here are experimental values, monoatomic gases. Here's CV. See, there are the experimentally measured values.
Why is the CV for the diatomic gases the same? Like, why aren't those all the same?
No, for the diatomic gases, it's not the same. Okay, for the diatomic gases, they have 5 degrees of freedom.
Right.
So it's 5 halves R. R is, so 5 halves R is 2.5 times 8.314, which is that.
Right, but what I'm saying is all the diatomic gases, shouldn't they have the same CV then?
Oh, yeah, I mean, okay, so there's, so this is a,
Because the atomic mass is different, or?
no. This is, we derived everything assuming it's an ideal gas. Ideal gas meaning these molecules don't attract each other and all that kind of stuff.
Okay.
Yeah. So, but there's plenty close.
Right.
Yeah, this guy doesn't behave ideally. Yeah. So, okay, so what we're saying is, these simple derivations are giving you the right results. They're at least giving you ballpark results. Okay. So CV. So we now know how to calculate heat added along this path because we have CV. Yep. Now what we're going to do is show you how much heat is added along that path. We're going to calculate CP, okay, for an ideal gas. We'll derive a number, and if in fact for the gas doesn't agree with that number, then that means that gas is not an ideal gas. Okay, so internal energy, change in internal energy was Q minus W. Q was change in internal energy plus W. And so let's say we started at absolute zero. Internal energy was 0. The amount of heat added is internal energy plus work. Okay, so all right. So if you add a small amount of heat, the small amount of heat added is the small amount of change, infinitesimal change in the internal energy plus the work done. Any work done. Any work done by a gas is that, PdV. Change in internal energy for an ideal gas arises because of change in temperature. Okay, and this guy gives you that. N times CV times delta T is that. dQ, so we're doing a process where the pressure is constant, and CP delta T. Okay. So PV equal to nRT is the ideal gas law. Here's a process where the pressure is held constant. So P delta V is nR delta T. This is equal to that. Okay. Delta T is common. Okay. N is common. So Cp minus Cv is R. Yeah. So what we have shown is for an ideal gas, Cp is greater than Cv by R. Yeah. So Cv, so now I'll write down the general expression. Cv was equal to F by 2R. What was F?
Degrees of freedom.
Degrees, number of degrees of freedom. So Cp is this plus R, so that works out to F plus 2 by 2 times R. So now you guys have expressions for Cp and Cv in terms of degrees of freedom. Okay. So what you have learned is You can calculate how much heat you're adding to the system along horizontal paths and along vertical paths. Okay? Can you calculate how much heat you've added along these paths, along a general path? Can you calculate the heat added along this path?
Not yet.
Not yet. Okay.
You gotta break it up.
Yeah, you just, so you're calculus experts, so you break it up into vertical and horizontal paths, pieces, and you can, in principle, calculate it. Yep. All right, so we define a quantity called gamma, which is the ratio of specific heats. Okay? And this is a useful quantity. And let me show you what it tells you. So gamma is, okay, so you see gamma is, so let's do this. So gamma is gamma is Cp by Cv. Cp is F plus 2 by 2 R. Cv is F over 2 times R. Okay. What is the least number of degrees of freedom a gas can have?
3.
And as the number of degrees of freedom tends to infinity, or large number, this becomes 1. So this is gamma, this is 1.67, okay? So for 3 degrees of freedom, gamma is 1.67, and for F equal to infinity, gamma is 1. So as gamma decreases, the particles are getting more and more complex. That's what gamma tells you. Okay? So you see here's gamma. For monoatomic gases, it's 1.67. For diatomic gases, gamma is reduced to that. For more complex molecules, gamma is lower. So here's a monoatomic gas, here's a diatomic gas. It has three translational degrees of freedom and these 2 rotational degrees of freedom at these temperatures. At very low temperatures, these degrees of freedom are not in play because it takes too much energy to excite them, and you don't have enough money to do that. Okay? And if you heat this even more, then you can get vibrational degrees of freedom as well. Okay? That can happen on the surface of the sun, for instance, or inside a furnace. Okay? Here's a complex molecule, okay, methane, and it has more degrees of freedom. So for a diatomic molecule which has F degrees of freedom, Cv is F is 5, is 5 halves R. Okay? And Cp by Cv for a diatomic molecule, Cp by Cv is 1.4. Okay? 5 plus 2 is 7 divided by 5. Okay? So CV is F by 2R. So this graph illustrates things quite well for you guys. So I believe this is for a hydrogen gas, which is a diatomic molecule. Well, it could be any diatomic molecule, but you can see that below 100 degrees of 100 degree Kelvin, that's quite cold. CV is 3/2 R. That is, the number of degrees of freedom is 3. It only has translational degrees of freedom. So those temperatures are too cold to excite the rotational degrees of freedom. At these temperatures, what is the temperature in this room? 300 degree Kelvin. This is temperature in Kelvin. So in room temperature, CV is 5/2 R. So all these molecules running around in this room have rotational degrees of freedom. Yeah. This is the surface temperature of the sun. At these temperatures, CV is 7/2 R. It has 7 degrees of freedom. 3 translational, 2 rotational, and 2 vibrational. Okay. All right, so we're sort of running out of time. I was going to do these derivations, but I'm not. Okay. So I'll say, again, our theme has been you have various processes happening, and we want to say what is constant. Okay? So that's giving you some information about a process. What is this process? It's an isothermal process. And what is constant in this process? Along the blue line, the temperature is constant. So if you take a gas along this line, its temperature will remain constant. Yeah. What is this process? An adiabatic process. So let's say you take a fixed amount of gas in a piston and you raise the piston, and there is no heat flowing into the system. So this is an insulated cylinder. Okay? So as the gas expands, it's doing work. Okay? So it needs energy to do work. Where did the energy come from? Internal energy. So it was using up the savings of its children. Okay? The internal energy decreased. So it cooled down. See, it cooled down. Okay? Well, the question is we ask, is there anything that's constant during this process? And we can show to you that PV to the power of gamma is constant. So you can take, for each point, P and V are different. So PI VI to the power gamma is constant. And here's the derivation of it. Unless you guys want to see it. Well, yeah. So PV to the power gamma is constant. And then you can also use that along with the ideal gas law. And you can show that this is the same as this. So V to the power of gamma minus 1 is also constant along that. So along this process, this is also constant. Okay. All right, so we said that. Okay, here's a slab of air. So here's the slab of air. Does it weigh anything?
Yes, it has mass.
It doesn't matter. Why isn't it falling down?
Because there's air below it, which is of a different density.
I'm sorry?
Because there's air below it that's also weighing something else that's different density.
Yes, so why isn't it falling down? Well, gravity is pulling down on it. So the force of gravity must be balanced. And so the pressure below must be higher than the pressure above. So pressure times area is this force, upward force, and there is the downward force. So this downward force must be less than this upward force. By how much? Equal to the weight of this thing. Okay? So dP, that is negative. The change in pressure as you rise up, pressure decreases as you rise up. Okay? So P equal to N over V RT. Okay, what we're going to do is we're going to assume that the temperature is constant as you go up. It's not true, but we'll assume that. So temperature is constant. So how can pressure decrease? Is the volume density of particles decreases. That's what Beth was saying. Okay? So pressure decreases because the number of moles per unit volume decreases. So the air gets less and less dense. Okay? And that's what's going on. In fact, okay, so there is the force at the bottom, this minus the force at the top should equal, this is the mass of a single molecule, this is the weight of a single molecule times the number of molecules there are in this slab. Okay, so weight of a single molecule, volume density times the volume of that slab. Yeah. And you can go through this derivation, and what you'll see is, the volume density, so this is the change in volume density divided by volume density is that. So the volume density, what that is N over V, N at a location Y is equal to N at location 0 divided by V e to the power of minus mgy kt. What is this fellow?
Potential energy here.
Potential energy of a single molecule at elevation Y, where it's 0 at ground level. Okay? So you see, the density decreases exponentially. Okay? At about 8.1 kilometers, okay, 8.1 kilometers is 5 miles. At 5 miles, this number becomes minus 1. So the density is 1 over E times that. You can do 1 over E, it's about 0.35. At 8.1 kilometers. So the density of molecules is about 35% the ground level density. Oxygen content is 35% of ground level oxygen. You guys know what is the height of Mount Everest? 9 kilometers. So it's less than that, about 30% or something like that. Yeah, so if somebody can climb Mount Everest without oxygen, that's pretty damn good. Planes fly at? Oh?
Some of them travel at 5.
11 kilometers. So there the density is about 20% ground level density. So you'd better pressurize the cabin, otherwise nobody's flying. Yeah. All right, so this leads to an important idea. See, E, this is potential energy divided by KT. Okay, so what Mr. Boltzmann was very smart. Okay, so let's say you have a system with a bunch of particles, yeah, and this is at a temperature T. This system is at temperature T. What Mr. Boltzmann came up with is the probability of this energy level being occupied is e to the power of minus EKT. Okay. So this gives you the probability of this energy level being occupied. You see, higher the energy, lower the probability of being occupied. So let me do this. Okay, so let's say, so these particles, let's say, can occupy only these energy levels. So what you'll have, the lowest energy level, there's the most number of particles at the lowest energy levels, and then less and fewer and fewer. Okay, so that's how the system will be. All right. What if the system is like this? This is, what is this saying? Equal probability of occupation of all these levels. When will that happen? When the temperature is infinite. So this means the system is at infinite temperature. All right, I'll tell you an even more mind-blowing thing. What is this diagram telling you? A higher energy level has a higher probability of occupation. That can happen if this was positive, but that's not positive. Very good, my friend. Very good. This is negative temperature. So this is what happens in a laser system. Okay, you have to figure out somehow to get more atoms in the excited state, higher state. So most lasers are two-level systems. You got to get that in higher state and then have them drop to the lower state and emit a photon. Okay. All right, so now you know what an infinite temperature and negative temperature means. All right. Okay.